All right, let's get started. So our next speaker is Perdikaris. So he's a principal research manager at Microsoft Research AI for Science. He is now physically located in Amsterdam. And currently he works on developing foundation models for weather and climate. And prior to this, he's an associate professor at the University of Pennsylvania. And he received his PhD in applied math from Brown in 2015. I was a postdoc at MIT 2015 to 17, and from 17 he's been at UPenn. So his research spans many aspects of computational science, including deep learning, physics-informed neural networks, neural operators, generative models, uncertainty quantification and decision making, and multifidelity modeling. Right. With that, Paris, thank you for joining us, and we are looking forward to your talk. Thank you.
Thank you very much, Karthik. Hello, everyone. Thank you for the invite. Good morning there. So today I have prepared for roughly an hour and a half of a presentation to give you an overview of some of the efforts that have kept us busy over the last year at Microsoft Research, which are around basically building foundation models for the Earth system, and specifically for modeling and predicting atmospheric dynamics. So let me start with some brief motivation, and today I'll try to cover the main results that we have obtained, and also some technical details on the architecture and the training pipeline and all those technical details and nuances that come into scaling up and building a foundation model in this setting. All right, so first of all, I don't think I need to really introduce foundation models to this audience. This whole workshop is about them, but basically, just in terms of terminology, a foundation model is just a large-scale neural network that is trained in two distinct phases. So there's a first phase, which we call the pre-training phase. And the goal of the pre-training phase is not really to build a model that is accurate for any task out there, but is really a phase that aims to help the model extract representations that are generalizable, sort of general purpose, from a very large corpus of diverse data. So basically, the setting here that foundation models are built on is the setting of transfer learning, in which in the first pre-training phase, the goal is to extract meaningful features and general purpose features from very large volumes of data. And then in the second phase, which is the fine-tuning phase, this base model will be fine-tuned to make accurate predictions in different distinct tasks, even in scenarios where training data for each one of those tasks might be limited. So it's going to leverage, basically, instead of training a model from scratch for each one of those tasks that we want to be able to predict, we will be starting from this pre-trained model and then fine-tune it to excel at some of those new tasks. And generally, this sort of framework has introduced a paradigm shift in machine learning over the last couple of years. And it's a paradigm shift that is sort of eclipsing the previous school of thought of basically building specialized deep learning models that are trained on a single data set and are aiming to tackle a single prediction task. So, since the Transformer paper basically came out around 2017, 2018, we see this consistent paradigm shift of moving away from specialized models towards this concept of foundation models in machine learning. And indeed, we've seen a lot of disruption in different fields. So most recently, there's the AlphaFold 3 paper released. So it's a foundation model for proteins and systems biology. Of course, all of you are familiar with the GPT systems from OpenAI, and also all the multi-model type of foundation models that combine text, images, audio, and other data modalities. And all of those have introduced very impressive results, and they're really disrupting different areas of science and engineering. So the main question that my colleagues and I at Microsoft have been thinking of over the last 2 years or so, and I know Aditya gave a talk on Monday on foundation models for climate. So everything started with a project we call Climax, and the main question was, can we also adopt this paradigm in Earth system science? And can we leverage the vast volumes of data that are available in this domain to also build a foundation model for the atmosphere and atmospheric prediction? And this is a very unique setting. If you think about all those different scenarios for which foundation models have led to success stories, there's two key ingredients there. So the first and most important ingredient is the availability of a lot of data, including also really high quality data. And of course, the second piece of the puzzle is scaling up these large deep learning architectures, throwing a lot of GPU capacity at them and training them at scale. And if you were to think, okay, if we're looking at the physical sciences, which are the type of applications that are sort of ready to be disrupted by this paradigm, meaning which are the application cases that for which we do have access to tons of data, well, the Earth system is a prime example because it's really unique in the way that it has been monitored over decades now and is generating exabytes of data. And just to give you a sense of scale, GPT-4 was trained on 75 terabytes of text data. And basically, this is pretty much the whole text you could access on the internet. Whereas in Earth system science, we're facing very diverse problems, but also really vast amounts of data in the order of petabytes or exabytes. And nobody has ever attempted to actually tap into this vast expand of data. So modeling the atmosphere, this is sort of like a very brief overview, and I'm not really an expert atmospheric scientist or meteorologist, but basically this is sort of the paradigm that up until now we have been adopting to understand nature in general. So this paradigm is formulated on first physical principles. People have spent a lot of time deriving equations that describe governing laws, conservation of mass, energy, momentum, the basic equations of fluid dynamics and thermodynamics, and using those equations to describe how the atmosphere evolves. And to do so, you have to basically account for very complex interactions across many different scales, the way that the oceans, the land, and the atmosphere are all coupled together. And you have to resolve different physical processes and different effects at different resolutions in order to build a predictive model. So there is centuries of history behind this, first principles in terms of physics and mathematics, and of course, over the last few decades, the advent of computing and the fact that we have access to very sophisticated supercomputers have enabled us to simulate atmospheric dynamics to a very high degree of fidelity and resolution over the entire Earth. So the current gold standard for predicting the weather is what we call numerical weather prediction, which is basically a sophisticated system that consists of two main modules, a forecasting module that solves an initial value problem. So given a set of initial and boundary conditions, it basically discretizes and solves the partial differential equations that describe this complex coupled system. And on top of that, there is another module, which is a data simulation module, through which the output of those numerical simulations is calibrated to real observations that we're collecting from weather stations and satellites and other remote sensing means in order to obtain accurate initial conditions for the simulators. And it's a very expensive pipeline. So it takes hours on supercomputers to be able to produce, let's say, a 10-day weather forecast around the Earth. And there's decades of development that have gone into this in order to reach the current state of technology. At the same time, one can argue that even the physics themselves are not perfectly known. So there's a lot of assumptions that go into building such systems. And those assumptions also lead to parameterizations that try to account for the things that we don't know. And also that adds to the cost of calibrating those systems to produce accurate forecasts. But this is the current gold standard and the sort of the current state of the art in terms of predicting weather. And now the promise of deep learning is to basically introduce a surrogate to this entire system. The holy grail would be to have a surrogate that sort of end-to-end handles the data simulation part and the forecasting part. However, up until now, most efforts have focused only on the forecasting piece. And today also I will be focusing on that. All right, so why do we think that foundation models could transform the way we model and predict the Earth system? First of all, as I mentioned earlier, this is a setting which is very unique in the sense that we have access to very large amounts of diverse, heterogeneous data across multiple scales in space and time. So we have observational data coming from satellites, weather stations, buoys, balloons, and so forth. But also we have access to historical data generated by simulation tools, so weather and climate prediction models. And those date back to the 1950s or 70s with variable levels of resolution and fidelity, and include ensemble forecasts, analysis data that combines the output of a simulator with a data simulation step to account for observations, and also reanalysis data that uses future observations to calibrate a past state of the atmosphere. So there is a range of tasks here. I'm sort of giving you a taxonomy more or less organized in terms of time scales. So starting from nowcasting, which is basically the task of predicting the weather at very short temporal horizons and at very high spatial resolution. So whether, it's going to rain in Ann Arbor in the next half an hour or not falls under this nowcasting problem setting. And nowcasting basically is dictated by deterministic atmospheric dynamics. So that's something we can simulate with high degree of fidelity if we have access to high resolution sort of simulators. It can capture, basically can address very local weather phenomena and questions. Then moving on to longer temporal scales, if we want to predict the weather, let's say from 6 hours into the future, maybe up to 10 or 15 days, which is sort of the window of predictability, we have to now start looking at more global effects, and we need to simulate the weather at the global scale because, within a range of a couple of days, the weather in San Francisco depends on how the weather was in other regions of the world a couple of hours or days before. So now we're talking about medium range weather forecasts, which is still sort of dictated by the evolution equations of atmospheric dynamics. However, the window of predictability sort of breaks between 7 to 10 days into the future because the system is very sensitive to initial conditions, which we can never perfectly estimate. So there is sort of chaotic dynamics, and therefore a probabilistic treatment becomes more necessary for longer term predictions. And this is how currently we predict the weather using ensembles of numerical weather prediction tools. Now, moving even further beyond in terms of timescales, we can think about predicting the weather a couple of weeks ahead or maybe a few months, which takes us to seasonal and sub-seasonal predictions, and maybe all the way up to climate projections to try to predict how the climate evolves in a timescale over years and decades as a function of different input and forcing factors that we're modeling. Now, beyond weather forecasting, there's a lot of other interesting tasks. For example, the task of predicting atmospheric composition and atmospheric chemistry that sort of determines how health, sort of air quality forecasts and other health-related warnings are issued. And now in this case, we're kind of departing from the setting of weather forecasting. We not only need to resolve convective weather transport phenomena, but we need to couple that now to kinetic equations that describe how different chemical species in the atmosphere interact. So the problem becomes increasingly more complicated. And also in this particular setting, this is a distinct setting in the sense that we don't have access to as many data for the coupled weather and chemistry system as we have for weather alone. And I'll come back to this task a little later because it's quite interesting from a machine learning standpoint. How do you approach such a problem for which you have some scarcity in the data that you're working with? So the hope and the hypothesis that we're having here is that by leveraging these large volumes of Earth system data, we could actually build a foundation model that can bring significant enhancements in flexibility. So basically, how can we actually set up machine learning tasks and build systems that can learn from all these heterogeneous data sources. And then we hope that if we're able to do so, we have a system that can generalize well and exploit transfer learning to address new scenarios and potentially also scenarios that are very limited in terms of data availability, such as atmospheric chemistry. And of course, finally, is the issue of performance. We would like to be able to outperform classical numerical weather prediction, not only in terms of speed, which is sort of the obvious one. Potentially with a neural network, you could make a 10-day forecast within seconds instead of hours on a supercomputer, but also accuracy. And this is a subtle point. But the subtle point here is that we have good indications that those deep learning surrogates could actually result and produce more accurate forecasts than the PDE-based models. And this is because they're not only trained on the PDE-generated data, but they're also trained and take into account observational data. So basically, by leveraging these high-quality reanalysis data sets for training, the machine learning system is exposed not only to the sort of physical structure of the problem, but also takes into account real observations. And I'll come back to this point a little later because it's a subtle point, but it's quite interesting because at the end of the day, those surrogates seem to be more accurate than the classical simulation tools we're using, at least in the domain of weather forecasting. All right. So today I'm going to focus on two areas. So we're not going to build a foundation model yet that tackles everything out there, but we're going to try to build a foundation model that tackles two different and very distinct prediction tasks. The first one is medium range global weather forecasting. So predicting the weather from a time horizon from 6 hours up to 10 days. And we'll try to do that at the highest resolution possible, which is roughly 10 kilometers globally at an operational setting. So our goal is to really build a system that competes with whatever current operational tools are out there for predicting the weather. And then the second task is quite more interesting because we're going to take this model that was trained on weather and try to fine-tune it and extend it to see whether it can actually also enable us to predict atmospheric chemistry variables, specifically the ones that determine the air quality forecasts. So to do so, we're going to build a model that we call Aurora. Aurora is sort of an extension, like a follow-up sort of effort from an initial model that was called Climax. So Climax was a first sort of academic proof of concept of a foundation model for weather and climate. And I'm calling it a proof of concept because it really focused on a much smaller corpus of training data, but also much lower in terms of resolution. So it was a tool that it didn't really aim to compete with operational weather forecasting tools, but it was just a first attempt to demonstrate the concept of a foundation model in this domain. So Climax basically was that effort took place in 2022 and 2023. And then we continued working along those lines to build Aurora, which is kind of like a scaled up version of Climax, both in terms of resolution, model size, data resolution, and so forth, with the goal of tackling atmospheric operational prediction tasks in atmospheric science. All right, so again, Aurora is a foundation model. It's going to be trained on two distinct phases. Phase one is pre-training, where we're going to take a collection of different data sources containing both forecast data, analysis data, and reanalysis data. And then we'll just try to feed all this data to Aurora and try to build a one-step prediction model. By one step, meaning that Aurora is going to receive as inputs the state of the atmosphere at time t and maybe at time t minus delta t, so 2 steps in the past. And then its goal is to produce a forecast for the next state of the atmosphere at time t plus 1 or t plus delta t. Typically, delta t here will be 6 hours or 12 hours into the future. So it's just a one-step predictor. This is sort of the training objective for the pre-training objective for Aurora. And the main goal here is to build a model that is flexible enough to accommodate all those different data sources. And the heterogeneity here comes from the fact that those different data sets will have different spatial resolution, may have different number of variables and types of variables, and also may include different number of atmospheric levels. So also the z-axis resolution along the height of the atmosphere may be different in each one of those data sets. So in order to accommodate this data heterogeneity, I'm going to later on give you a description of what is the encoding mechanism that we have designed to basically process inputs with different resolutions and arbitrary variables and pressure levels. and convert them into the standardized latent representation in a three-dimensional grid that can then be processed by a vision transformer, a three-dimensional vision transformer. And then finally, we'll have a decoder module that takes this latent representation and decodes it back to produce the forecast at time t+1. So essentially, you could think of this as an encoder-decoder model. The encoder has to be very flexible in the way it processes the inputs. The backbone, which is this three-dimensional vision transformer, learns essentially a time integrator in the latent space, and then a decoder maps the latent representation back to the target outputs. And the pre-training here is going to take, it's an expensive process. Specifically for Aurora, the largest version of Aurora was 1.3 billion parameter model, and we pre-trained it over a period of 2.5 weeks using 32 A100 GPUs. Now, the second phase is the interesting one because, in the first phase, we're not trying to solve a particular task, but mainly we're trying to take all these input data sets and compress them inside the weights of this transformer model. And the second part of training, which is the fine-tuning part, we're going to have specialized versions of this Aurora model that are specifically trained to excel at a specific forecasting task. So we have 3 tasks that I will cover today. 2 of them have to do with operational weather forecasting at different resolutions. So we'll have operational weather forecasting at quarter-degree resolution, which is roughly 30 kilometers or 28 kilometers resolution at the equator. And this is a setting where all existing AI tools up until now have been built, including GraphCast and ForecastNet and Pangu Weather. The second task will be operational weather forecasting at higher resolution, at 0.1 degrees resolution, which is roughly 10 kilometers globally. And again, this is something that, as we will see, is a byproduct of this foundation model approach. So, and I'm going to go into the details on that. And then finally, we'll revisit this atmospheric chemistry prediction task and try to build a model at 0.4 resolution around the Earth, which is roughly in the order of 40 to 50 kilometers globally, to model atmospheric chemistry and produce air pollution forecasts. Now, the fine-tuning phase is cheaper than the pre-training phase. It roughly takes 1 week on 8 GPUs. And in this phase, we are using a technique called low-rank adaptation, which is a fairly simple sort of parameter-efficient technique in which we're not going to update all the parameters in this model, but instead we will just fine-tune a smaller subset of those parameters. And I'll share more details about this LoRa adaptation part later on. So for now, I just want you to kind of remember that there's those 2 distinct phases, pre-training on weather data, and then fine-tuning at different to excel at different tasks. And what we're basically learning here is an autoregressive simulator. So the inputs to this model will be the state of global weather variables at time t and maybe time t minus delta t. And then we're going to learn a map from these inputs to the next state of the atmosphere at time t plus delta t. And if we want to now use this surrogate to produce longer trajectories, so predict those states further into the future, we're going to evaluate the surrogate autoregressively. So we'll take the prediction at t plus delta t, feed it back as an input to the model to get the prediction at t plus 2 delta t, so on and so forth, to get forecasts up to 10 days into the future. All right, so we'll start from presenting some results, and then towards the end of the presentation, I'm going to go more into the details about the architecture itself and the training pipeline and the technical pieces. So these are the set of results, and I'm going to start with the task of atmospheric chemistry and air pollution, primarily because it's the most novel one and maybe somewhat surprising as well. Then we're going to talk about high-resolution global weather forecasting, and then I will cover some results on model scaling and how the data diversity helps with generalization in the setting. All right, now before I go into those tasks, let me just give you a quick overview of the types of weather data that we used to pre-train Aurora. So Aurora was pre-trained on a mix of weather data sets, including forecast data, which is the direct output of numerical weather prediction simulators, of analysis data, which is again simulation-based, but also includes an assimilation step of observational data from the past in order to calibrate the initial condition of a simulator. Reanalysis data that is employing also data assimilation of observations, but also including now observations from both the past and the future to calibrate the initial condition of a simulator. And again, reanalysis data cannot be, so a reanalysis product cannot be used at an operational setting because it involves knowing, the state of the atmosphere in the future, which is not available in an operational setting, but it's something that we can leverage from historical data to build these deep learning tools. And this is the highest quality of data available because it sort of encapsulates our best understanding of the atmosphere in the past. And this is really the key step and the key reason why those deep learning tools could be more accurate than the PDE-based tools, because they're trained on this reanalysis data that not only includes the physics-based knowledge that the PDE model represents, but also includes knowledge about the observations and this calibration step that is performed. Finally, there's observation data, but in Aurora, in training Aurora, we did not directly employ any observations data. So we mainly leveraged forecast analysis and reanalysis data to train the system. A little bit about pre-training. So this is the mix of data sets that were used to pre-train Aurora. You see on the left-hand side the different names. So that includes reanalysis data like ERA5. It includes forecasts data from the IFS system in Europe, which is considered to be the gold standard in numerical weather prediction. Also includes forecast data and analysis data from the GFS system, which is the system used in the US, developed by NOAA. Also uses some lower resolution and lower fidelity climate simulation data sets, such as the IFS-HR and the CMCC data. Uses even lower resolution data from NASA called the MERA-2, which is also a reanalysis product. And the main thing to notice here is that all those data sets come to with different spatial resolutions. So the resolutions here range from quarter degree, which is roughly, again, 30 kilometers over the equator, to 0.625 degrees. Each one of those data sets, again, has different resolution across the atmospheric levels, so the heights in the atmosphere. So you see some data sets have 13 atmospheric levels, or 3 or 7. And then each data set may have a different number of variables. So we have a collection of surface variables, including the surface temperature, the U and V velocity components, the mean sea level pressure. And then we have a collection of atmospheric variables, including, again, wind velocity components, temperature, specific humidity, and this geopotential variable denoted by Z. And again, different data sets have different number of variables and also span a different time period, with the largest data set here being ERA5, spanning the period of 1979 to 2020, another data set spanning, different periods, as you see here. So Aurora basically was pre-trained on this weather data. The highest resolution in the pre-training data set was quarter degree. And it would have a total basically of 1.2 petabytes of data here, roughly corresponding to 11 million data pairs. And by data pairs, I mean, 2 previous atmospheric states and being as taken as an input, and 1 atmospheric state taken as an output, with the a delta T, basically a lead time of 6 hours. So within those 11 million data pairs, Aurora is exposed in different factors of variability, coming from different parameterizations of the physics themselves, because each one of those models sort of has a different parameterization and different physical assumptions. Of course, variability due to different initial conditions being used, variability due to the chaotic dynamics of the atmosphere. So one of the main motivations here is behind using different data sources is that we want to build a model that has been exposed to all those different sources of variability. And we hope that by doing so, it can sort of average out any biases that each one of those data sets may contain and generalize better when it comes to making predictions. So the goal of pre-training is to learn a general purpose representation of atmospheric dynamics out of all these data sources. And basically the model was trained on roughly 2 to 3 weeks on 32 A100 GPUs. And we actually used the subset. We didn't use the entire 1.2 petabytes, but we experimented through different ablation studies with using selected subsets of all this data for the pre-training. And I'm going to talk more about those data ablations later on to sort of try to get some intuition about the effect of different data sources in the setting. Now, once the model is pre-trained, we're going to go ahead and fine-tune it. And the first task that a fine-tuning task that I want to cover is this task of atmospheric chemistry and air pollution. And I think it's one of the most interesting settings for which we have deployed Aurora, because this is a task that encompasses many of the challenges that data-driven models face. And these challenges include data scarcity, because in the setting of air pollution, we don't have access to a lot of high-quality data that we can leverage. Data heterogeneity, I'll show you some example of what I mean about that later. And of course, the main and most interesting piece here is that now we want to take a model that was pre-trained on weather data, so basically atmospheric.
So Paris, there is a quick question.
Sure.
So I know you said when you pre-train, you basically predict one step at a time. But the question asks, when you predict future variables, do you predict step by step or predict multiple steps?
No, we predict one step at a time. Also, when we do, rollout forecasting over 10 days, we evaluate the model step by step with a lead time of 6 hours or 12 hours.
And it's always, what is the time step? Is it an hour, minutes? What is it?
It varies from one task to the next. For weather forecasting, we use a time step of 6 hours. For this chemistry prediction task, we use a time step of 12 hours.
Okay, all right, thanks.
All right, so basically the main point here I wanted to make about this chemistry task, it is very interesting from a modeling standpoint, because as I mentioned, Aurora is pre-trained only on weather data. And now we're basically asking the question of, can we actually fine-tune it on a totally new scenario for which the physics is totally different, because now the physics involves all the kinetic equations of atmospheric chemistry. Will the model be able to pick this up and produce accurate forecasts for atmospheric composition? So this is one of the main sort of tenets of transfer learning, right? So we're building a model on one domain, which is weather, for which we have access to lots of high quality training data. And then we want to deploy it and fine tune it on a new domain, which is atmospheric chemistry, for which we do not have access to a lot of data. This is a setting that is almost hopeless to build a machine learning model from scratch, because there is scarcity, basically, of training data. And the question is, if we do this, if we fine-tune Aurora in the setting, how well does it do? Could it actually get close to reproducing the forecasts of current operational systems like CAMS? So CAMS is a Copernicus atmospheric monitoring system developed at ECMWF, which is the European Center for Weather Forecasting. And CAMS is an extremely expensive simulator, because it has to couple atmospheric transport and chemistry, and is roughly 10 times more expensive than a weather simulator. So of course, there is a motivation here to build a very fast and cheap surrogate for this expensive system. So here's how we go about fine-tuning Aurora in the setting. So as I mentioned, we pre-train Aurora on this mix of weather data sets. Now that was the first piece of training Aurora. And now in the fine-tuning stage, we're going to provide some data coming from atmospheric chemistry. So we're going to use two different data sets, the CAMS reanalysis data and CAMS analysis, spanning different time periods from 2003 to 2021. And what is interesting here is, in the setting of atmospheric chemistry, it turns out that the reanalysis product is not as accurate as the analysis product, which is sort of like the opposite situation compared to weather forecasting. So reanalysis uses a much older version of the underlying simulator and operates at a lower resolution, and therefore is a lower fidelity, basically, forecast compared to CAMS analysis. And basically, this is sort of the information that we got from the experts at ECMWF. So the goal is to basically reproduce and build a surrogate for this CAMS analysis product. But the issue here is that this product is undergoing constant updates from one year to the next. And basically, the only high fidelity data one could use span this period from 2017 up until now. So basically, we chose to use the subset of 2017 to 2022 to fine-tune, and then use data from 2022 and 2023 to evaluate and test the model. Now, in addition to the weather forecasting variables, so wind velocity, pressure, temperature, and so forth, now we have additional atmospheric composition variables, so including things like sulfur dioxide and ozone, and these particular matter variables, nitrogen oxide, and so forth, both at the surface and at different atmospheric levels. And again, you can sort of contrast the size of the data that is used for fine-tuning, to the 1.2 petabytes that we had for pre-training. Here, roughly, we have 5 terabytes of data that we're fine-tuning on. So a much, much smaller set of data in this particular task. And the cost of fine-tuning is also quite smaller. It takes about 1 week on 16 A100 cards. Finally, once the model is fine-tuned, we're going to go ahead and evaluate it against CAMS analysis data at an operational setting using operational initial conditions at 0.4 degrees resolution. And we're going to just pick a period of 6 months from June 2022 to November 2022. Let me talk a little bit now about the challenges of building a surrogate for atmospheric chemistry. First challenge is, as I mentioned, data scarcity. So high fidelity data do not date back to the 1970s. Unfortunately, they only date back to 2017 or 2018. There's multiple updates in this CAMS simulation tool as well. And those updates inevitably lead to a distribution shift. So the data that has been produced by those simulators is quite different from one update cycle to the next. The variables themselves are also quite peculiar in the way they behave. And here I'm just plotting a visualization of nitrogen oxide over the Earth. And you see here that we have very spiky behavior in regions where there is sort of intense human activity. So major cities in Asia and the East Coast of the US. And also then you have background levels corresponding to diurnal cycles, because nitrogen oxide gets, there's different physical processes taking place, that there's absorption of this species over throughout the day, basically day versus night. So now building a machine learning model in this case, where you're dealing with these concentrations that have very spiky values, you also have to capture these background levels. You don't have access to a lot of data. There's a lot of distribution shifts in the data set themselves because of all these different versions of the simulators that produce this data. Introduces a lot of challenges for building a machine learning system. And it almost makes it impossible to train a model from scratch, at least training a deep learning model from scratch in this setting, due to the data scarcity and all those challenges. Here's a summary of some results. So after we fine-tune Aurora and we evaluated, this scorecard here is basically measuring the performance of Aurora versus the CAMS analysis product on the evaluation data set in 2022. And basically every pixel here that you see corresponds to a single variable at a given pressure level in the atmosphere and a given lead time. So the horizontal axis is the lead time from 12 hours all the way up to 5 days. And basically what you see here is the relative root mean squared error of Aurora minus CAMS normalized by CAMS. So it's a relative error. And basically wherever you see blue, that means that Aurora gives a more accurate forecast than the operational CAMS product. And wherever you see red, it means that CAMS still outperforms Aurora. Now, in terms of summarizing these results, I should say, basically the summary here is that Aurora seems to be competitive overall with CAMS. Competitive here means that we are within 20% of RMSE on roughly 95% of all targets. So basically across all variables, all pressure levels, and all lead times. And Aurora matches or outperforms CAMS on 74% of these prediction targets. An important point here that sort of disadvantages Aurora is that we're not really using any emission data as inputs. And of course, emission data is very important. Basically captures the effect of anthropogenic factors in air pollution. And the reason we were not using them because we could not find sort of reliable sources for this type of data. So instead, by training Aurora on historical data coming from CAMS analysis and reanalysis, we're trying to implicitly learn the effect of those emission factors from those data sets instead of explicitly modeling them as inputs to the model. And that is one area for improvement. So I believe that if we find a way and to have high quality emission data and use it as inputs for Aurora, this picture might also change to basically favor Aurora a little bit more. Another area you see here, Aurora sort of underperforms CAMS in very short lead times. And this is primarily due to the fact that, you know, the CAMS forecasts and the analysis product are closely matching each other at very short lead times. And also we are underperforming CAMS high up in the atmosphere. So you see here in the temperature, the specific humidity and geopotential, and also in the ozone variables, CAMS returns more accurate predictions. It's not entirely clear why this happens, but we sort of postulate that sort of the quality of the data that we have at those atmospheric levels may not be sufficient for building an accurate deep learning system. But the main selling point here is that, you know, CAMS takes almost a day on a supercomputer or more than a day to produce a 5-hour forecast, whereas Aurora takes roughly 6 seconds on a single GPU. Of course, this is just the inference cost. We also have to factor in the pre-training and the fine-tuning costs, which is a few weeks. But these costs are sort of one-time costs, right? You pay them once, and now you have a surrogate that is extremely fast and can produce those 5-day forecasts within a few seconds. This is just sort of like a summary of the performance. Another plot to sort of illustrate this. It's the same message here. Yeah.
Can I ask a quick question on the previous one? So, yeah. I mean, there's always this trickiness when you compare machine learning models, right? That you only count the inference cost, and you sort of pointed out that the pre-training and fine-tuning is one time, but most likely the pre-training is one time, but the fine-tuning may not be one time, right? Because as you get more data, right, so you'll have to amortize you probably are fine-tuning as new data is coming in, right? Every, I don't know, so many, months or so many, quarters or whatever, right? So how do you sort of, is there a sort of more fair way to do that, that inference plus fine-tuning cost versus sort of traditional models?
I mean, it's hard to do that because at the end of the day, we'll never be comparing apples to apples, right? So, you know, it's also different hardware. There's, you know, a lot of differences that characterize the two approaches. But I think that, you know, if we were to use this tool in an operational setting, that it needs to be evaluated on a daily basis, then, you know, the cost of the AI system at some point, it breaks through, right? So you're gonna get cost savings or a speed up if you were to use this tool on a daily basis. In terms of updating, I would say that the pre-training doesn't need to be updated very frequently. You may want to update it once every year or two because of the changing climate. So you're kind of like capturing the most recent behavior. Fine-tuning also doesn't need to happen that often. So you want to fine-tune for specific prediction tasks, maybe as new data comes in, but I don't think you need to do it more than once per year or twice per year either. So yeah, that's basically my estimation on this. So yeah, there is some cost on pre-training, but you pay that once every year or two, and that is like 2.5 weeks on 32 GPUs, which is not outrageous. And then there is some cost for fine-tuning that also you're gonna pay once or twice per year. It's another week on 16 GPUs, which is again not outrageous. And then once you pay that cost, you have a tool that you can interact with almost at real time and produce forecasts at, within a matter of seconds on a single GPU card. So I think overall that the footprint of the cost is more advantageous for the machine learning model in this case.
Yeah, thanks.
All right, so I'll just quickly skip this one. It's just the same plot as before, like same result, but plotted in a different way. Again, you have this horizontal line at 0%, which is the relative error of CAMS itself. And basically that shows again that Aurora basically shows the relative RMSE of Aurora versus CAMS at the 3-day lead time mark. So if you see that the green line is below the red dotted line, that means that Aurora has a more accurate forecast, except for those variables at the far right. But this is also meant to show that Aurora doesn't really learn to predict something trivial. We're also plotting the persistence prediction, which is basically a very naive prediction, assuming that nothing changes from one time step to the next. This is the black line indicating that, this is sort of like a trivial prediction. So again, the take-home message is that the 3-day mark, Aurora is competitive with CAMS or outperforms it on roughly 86% of all variables. And to us, that was quite surprising and quite impressive because this is a task that comes with a lot of challenges, comes with a very scarce collection of data sources, and being able to just quickly fine-tune a model that is pre-trained on weather to make these atmospheric chemistry predictions is something that, is somewhat mind-boggling, right? So again, this is the first step, but that shows the promise of the foundation model approach in this setting. Here's another result. We also looked at the performance and the ability of Aurora to capture different extreme events. That was a sandstorm event that existed in our test dataset in 2022. And what you see here in every row, top row is the prediction of Aurora, middle row is the operational forecast product from CAMS. And finally, on the bottom row is the CAMS analysis product that combines the output of the simulator with the data simulation step for the initial condition. The take-home message is that all three models can sort of CAMS analysis being the ground truth, meaning here that, if CAMS analysis is the ground truth, both Aurora and the CAMS forecast can capture this event. The CAMS forecast is more accurate than Aurora, as you can see here by the plotted RMSE. But the take-home message is that was sort of like a spiky extreme event in the test data set that Aurora could capture, so it can predict that the storm is going to happen, but it sort of misses the magnitude of the target variable here, which is a particular matter variable. And that was one event in a series of devastating sandstorms that hit the Middle East in the spring and early summer of 2022 that led to like more than 5,000 hospitalizations in that area. All right, so that concludes the results I wanted to show on the atmospheric chemistry piece. Now let's switch our attention to global weather forecasting. And as I mentioned, the current gold standard is set by the Integrated Forecasting System, IFS, developed by CMWF. Since 2016, this system operates at a resolution of 9 to 10 kilometers globally, so 0.1 degrees. And building an AI system or an AI surrogate in this setting is also extremely challenging due to the following reasons. First of all, again, we're facing data scarcity. Whereas the quarter degree data that most people are using when building AI models date back to the 1950s or 1979 for the ERA 5 reanalysis product, 0.1 degree data are only available for 2016 onwards. So we did not have simulators operating at this analysis resolution before 2016. And a reanalysis product does not even exist to this date. The second piece here is just the sheer volume and complexity of the data. So a single data point, just a single state of the atmosphere, is roughly 2 gigabytes, occupies 2 gigabytes of memory. And that presents a stress test for all components of a machine learning pipeline, from data storage to data loading to building a model that can actually receive high resolution images as input. And that's the primary reason why we haven't seen yet machine learning models being extended to the setting. and all existing machine learning models out there tend to operate at a 1/4 degree resolution at the maximum. So the main research question that we were asking ourselves here is that can we pre-train Aurora on low resolution weather data up to 1/4 degree resolution, which is again up to 30 kilometers globally, and then try to fine-tune Aurora on this scarce subset of 0.1 degree data to unlock this new capability of high resolution forecasting. And I see there's another question.
There are a couple of questions, but I think those can wait until.
Okay.
Actually, yeah, I think one you can answer right now. Another one you can take later. Are there results about how well Aurora predicts extreme events?
Yeah, I will get to that in a second. That's part
Okay.
of some of the ablation studies we have. So I'll
Alright,
show
great.
some results on extremes. Yeah.
Sure.
Great. Okay. So the main question here is, can we pre-train this foundation model on low resolution weather data and then fine-tune it to make high resolution forecasts? So fine-tuning will here take place by using this IFS HRES analysis data on 0.1 degree resolution. And we're going to use data from 2016 to 2022 to fine-tune. This is roughly 20 terabytes of data. And then we're going to use the year 2023 to evaluate the performance of our model. And the fine-tuning cost for this task is very similar to the atmospheric chemistry. It roughly took 1 week on 16A100 GPUs. And again, yeah, the evaluation dataset will be the same dataset, HRES analysis, but in the year of 2023. And this is now the scorecard that measures, sort of like summarizes the performance of Aurora versus the IFS HRES system evaluated using in an operational setting, using operational initial conditions for both models. And we see a quite encouraging picture here. So basically, Aurora outperforms operational HRES on over 92% of prediction targets. Again, the x-axis here is lead times. So from 6 hours all the way up to 10 days. The vertical axis is different pressure levels for those different variables. And the bars below is the corresponding surface level variables. So UV velocity components of wind, mean sea level pressure, and 2-meter temperature. So quite impressive. The performance gains are most pronounced at lead times more than 12 hours. So at short lead times, again, IFS is more accurate. And again, this is because the IFS forecast and analysis product are more or less agreeing with each other at a very short lead time. And again, the inference cost is a lot lower. So IFS, if I remember correctly, takes roughly about an hour and a half on 300 CPUs, whereas Aurora takes a single second on a GPU. And again, everything here is at 0.1 degree resolution, so 10 kilometers globally. Now, beyond, so this comparison was against the IFS product, which is a gridded product, as a simulation output, so IFS analysis. We also tried to make a comparison against weather station measurements because weather stations sort of capture a more accurate picture of how we feel the weather on the surface of the Earth. So this is 2 different metrics, the mean absolute error and the root mean squared error for wind speed. Wind speed was not a variable that we used to train or fine-tune Aurora, but it's a variable that can be sort of derived or calculated from the UNV components of the velocity field. And here we're comparing against, again, the Aurora predictions versus the IFS HRES predictions against weather station measurements in 2023. And basically, we're averaging over all those weather stations and over all the times of the year that those measurements were collected, and just report this aggregate metric for wind speed. And the take-home message here is that Aurora outperforms IFS for both wind speed and temperature forecasts across all lead times up to 10 days. Another interesting case study that we looked here, and that goes back to the question on extreme events. There was a recent paper that was published in Nature Atmospheric Science that was benchmarking different AI models for weather forecasting. for this specific weather event, which is called Storm Ciarán. So Storm Ciarán was a weather system, a low pressure system that hit the western coast of Europe, so Ireland and the UK and the Netherlands in early November 2023. And from a meteorological standpoint, it was a very rare event in the sense that it was the lowest pressure that ever has been recorded in November in the UK. So from, to the eyes of a meteorologist, this is very rare because, they have never recorded a lower pressure at that time of the year in the UK. However, to the eyes of a machine learning system, that may not be so rare in the sense that similar events like this may have happened in other places of the world and historically, dating back to the 1970s, in terms of sort of pattern recognition, it seems like the machine learning systems can pick up and make predictions. However, what was interesting here in this study of Charlton and Perez that was published a few months ago, they show that although the AI tools were able to capture most variables of interest, they were not really able to capture this onset of maximum wind speed that occurred on November 2nd. So that was basically a rapid increase in the wind speed that sort of characterizes the intensity of the storm. And all existing machine learning models were under predicting that. So Pangu, GraphCast, ForecastNet, they were sort of like missing that spike in wind speed. So what was interesting here is, one of the questions that we asked ourselves, okay, we have a model now that can operate at higher resolution. So GraphCast, Pangu, and ForecastNet all operate at quarter degree. Does this higher resolution help with resolving more extreme events like this one? And it seems that to some degree, the answer is yes. So the 0.1 degree Aurora model that we trained actually was able to bridge this gap and return a forecast that is closer to the sort of the ground truth that the IFS analysis system was produced for this event. So here you see an evolution of the maximum wind speed from November 1st to November 2nd. And you see that the maximum value that was recorded from the IFS system was 35.2 meters per second. And then Aurora basically got quite close to it, forecasting at 32.6, whereas all the other machine learning models were roughly forecasting a value of 25 meters per second for this case. So that's just like an interesting case study that highlights some of the deficiencies, let's say, of the AI models in this setting. And it's quite interesting to see that, the performance of Aurora was actually quite encouraging in this setting. And we sort of attribute or hypothesize that this is maybe due to the fact that Aurora operates at a higher resolution, but also leverages a more diverse collection of training data, and that yields, more robustness towards those extreme events. But I have a more detailed ablation study on extremes coming up, so we can talk more about it then. Is there a question, or should I move on?
I think, yeah, there are a few questions, but they're not very specific to what you're showing. So I think it's probably better, when we move to the discussion part, or actually before the second part of your talk.
Sounds good. All right. So speaking about data diversity, I want to start showing a few of the ablation studies we performed to try to understand the effect of different data sources in the performance of the model. So we're going to start with a baseline case in which we are going to show the performance of a model that is only trained using their ERA5 reanalysis data. And this is sort of the standard setting for all AI models developed in this domain. So GraphCast was trained on ERA5 alone, Pangu was trained on ERA5, ForecastNet, and so forth. So we're going to start with taking our 1.3 billion parameter model and then pre-train it on ERA5. And that will be our baseline. So we're going to compare errors relative to this baseline model. That's why you see that the errors here are all kind of normalized to 100 in this case. So the y-axis is plotting relative RMSE, normalized by this ERA 5 alone baseline. And we're going to call this case C1. So we're reporting here a relative error for the surface variables on the left, and a relative error for all averaged over all variables for different pressure levels. So ranging from high up in the atmosphere, which is pressure level 50, all the way to pressure level 1000, which is closer to the surface of the Earth. So on the right-hand side, we're going to be averaging over all variables, but showing the errors across different pressure levels. Case number 1, we're going to take a model that is pre-trained on ERA 5 and also add some low-fidelity data to pre-training. So this low-fidelity data come from low-resolution climate model outputs from the CMIP6 family of climate models. So specifically, we're going to use the CMCC data and IFS HR data, which again, these are considered to be low fidelity, low resolution weather data. What is interesting here is that by adding this low fidelity simulation data, we get a better validation performance, which is a little bit counterintuitive. Validation here is still measured against ERA 5. There's no fine tuning. This is only at pre-training. So we pre-train a model on ERA 5 alone, use it as a baseline, and then pre-train this model C2 that is ERA 5 plus this low fidelity data. And we're measuring relative RMSE validated against ERA 5. And the surprising fact here is that by just adding this low fidelity data, we get an improvement in generalization, except for the 2-meter temperature variable at the surface of the Earth, in which case now the performance is worse. So that's one surprising fact, that adding low fidelity data improves generalization. Then we tried another subset that we take case 2, so ERA 5 plus low fidelity data, and on top of that we include data from the IFS ensemble, IFS forecasts, and then the IFS ensemble mean, all at 1/4 degree resolution. So the message here is that adding even more simulation data seems to improve performance further on most surface variables, except for 2-meter temperature. And for 2-meter temperature, there is a discrepancy between reanalysis data in ERA 5 and then forecast data in IFS. And that's the reason why we see, I think, this discrepancy for 2T here. However, the take-home message is that that seems to improve performance. So using this additional simulation data seems to improve performance specifically for the pressure levels for which the IFS ensemble data was present. So IFS ensemble data was only available from pressure levels 500 to 1000. So there you sort of see a consistent improvement in performance, whereas maybe in some other pressure levels for which we didn't have IFS data, the improvements are not so significant. Another case is case 4, which basically we take case 2, which is ERA 5 plus low fidelity data, and now we include forecasts and analysis data, but only up to 1 day, whereas in C3 we include the entire trajectory up to 10 days. Now we only include analysis and forecasts for 1 day. So the hypothesis here is that this C4 data set is higher quality than C3 because, you know, these short lead times, we sort of trust them more, right? There is no variability due to chaotic effects in the longer lead times. So C4 is basically the same as C3 in some sense, but using higher fidelity data for short lead time weather prediction. And it seems that actually C4 achieves the best overall performance with improvements across the board by leveraging good coverage of the entire atmosphere and also using analysis data from both the IFS system and the GFS system. So I think the take-home message from this case study is, on one hand, that diverse data helps with generalization, and even low fidelity data alone makes predictions more robust and improve generalization. And the second take-home message is that the quality of the data is also very important, and that is sort of highlighted between the difference that you see between C3 and C4, basically using a more high-quality collection of data sources in C4 leads to consistent improvements in forecasting accuracy. And that's sort of like the first time someone has done an ablation and tried to train a machine learning model across different diverse data sources. And there's a lot more to be done here. Of course, running those ablation studies is very expensive because basically every single case here involves pre-training a large model. But there is a lot more to be done, I think, in this setting, and more insights to be extracted. But that's sort of like a first step here. A second set of ablation studies was specifically on looking at the performance of Aurora and the effect of different data sets in predicting extremes. And the way we measure that is by computing thresholded versions of a root mean squared error that sort of captures the root mean squared error out in the tails. So 0, 1, 2, 3 standard deviations away from the mean. And then what you see here is the relative performance of Aurora, starting again with a version of the model that was pre-trained only on ERA 5, and then looking at the effect of adding additional data sets. Again, we have the C2 case, which is ERA 5 plus low fidelity, C3 case, which further includes 10-day forecasts from the IFS ensemble system, and then C4, which includes more high quality forecasts only up to 1 day lead time from the IFS and the GFS systems. And again, you see sort of a consistent picture that C4 is still the most accurate when we're looking at these thresholded metrics, and the performance at extreme events improves thanks to this diverse training dataset mix. So the take-home message is that pre-training on diverse data sources improves the forecasting of extreme values, at least at 6-hour lead time that we're looking at here, across all variables, all surface variables of interest. So 10 and the UNV component of the velocity, 2-meter temperature, mean sea level pressure, and also this derived quantity, which is the wind speed. That is not a variable that we trained for, but it's a variable that we compute from the UNV velocity components on the surface of the Earth. And as you see, anything that is below this blue line indicates better performance compared to this ERA 5 baseline. All right, so I think that sort of addresses the question on performance on the extremes, or at least what is the effect of data diversity on extreme event prediction. And I think the message is fairly clear that data diversity introduces an improvement in forecasting accuracy, both for typical weather events, but also for extremes. Finally, since we're talking about foundation models, we try to produce kind of like a rudimentary version of a scaling law. Again, it's very expensive to compute those scaling laws, and unfortunately, we didn't have access to a ton of GPUs and compute to do a more thorough investigation here. But what you see here is 2 different versions of Aurora, and actually now we have 4 of them, but this plot is a little bit outdated. So basically shows the validation loss on the HRES dataset. So we pre-train a model on ERA 5 and evaluate it on the IFS HRES data, and shows basically here the validation loss on the left as a number of GPU hours. The middle plot shows the validation loss as a function of the number of tokens. And finally, the validation loss as a function of model size in terms of parameters. So we have 3 different models, sort of like a tiny Aurora model with 113 million, a medium-sized model with 660 million parameters, and then our basically main model, which is the largest one with 1.3 billion parameters. And what you see here is that bigger models obtain lower validation loss for the same amount of GPU hours. So these results sort of suggest that we should be biased towards using bigger and bigger models because those train more efficiently. So if we fix a computational budget, we're going to be able to achieve a lower validation loss if we use a bigger model. So that's a result that is in agreement with what we see in vision and language. So these scaling laws seem to also hold up in this setting. We see sort of somehow predictable performance improvement as the model size is increased. So there's, again, a toy version of a scaling law here that we fit an exponent of minus 0.73. That indicates that every time the model size is doubled in terms of number of trainable parameters, we observe a consistent improvement of about 5% reduction in the validation loss. And we didn't have the budget to see where those scaling is going to saturate, but I believe that it should continue for quite a bit more if we scale the model size more and we increase also the volume of the training data. So yeah, we still don't know what is a compute optimal setting in terms of data volume and model size. That's something that we still need to investigate, but that's again a first glimpse of a scaling law for this foundation models for in atmospheric science. And I believe that this is the main results that I have. Okay, I have
Paris,
another. Yeah.
maybe we can talk a little bit about that scaling law. We will have a tutorial tomorrow afternoon on scaling laws. So this is very nice. So how confident, shall we be about these scaling laws, right? Because these models that you have at those parameter scale, right, may not be compute optimal, right? And if you sort of look at and of course, if you look at the Kaplan work or the Hoffman work, right? So there's sort of two angles to it, and so that's the first question, and then the second question is, your exponent actually is pretty close to what other text transformers are seeing, right? Around 0.1-ish for for the scaling exponent. So yours is also quite close with 0.07. I think it's 0.09 there, and it seems to generalize across various kinds of modalities and various kinds of data. So I'm curious if it's just a coincidence or maybe there's something happening with that exponent that we don't yet fully understand.
Yeah, I mean, it's hard to answer this question. What I'm showing here is also models that we kind of, again, due to compute budget constraints, these are not fully trained models. So we compute the scaling at the 5,000 iteration mark at pre-training. So I wouldn't be like 100% confident of, there's a lot of like knobs one can tweak here. So that's why I call this a rudimentary result. It's not fully conclusive. But yeah, indeed, this is a computer vision task at the end of the day. We're taking a bunch of high resolution images as input and we're trying to predict another image as an output. So we would expect to see the scaling laws observed in vision transformers to also hold here. I don't see the reason why we shouldn't anticipate this.
The tokens, wouldn't the number of frames matter rather than how big a frame is? Wouldn't that be the better parameter for tokenization, surrogate for tokenization?
So for the middle panel, you mean?
Yeah.
So
do you have a rough idea how many frames you have?
Yeah, but the frames also have variable resolution. So yeah, I'm not sure.
Okay.
So yeah, I guess here we report number of tokens. I think this is sort of like a standard. If you look at scaling law papers, usually the x-axis is number of tokens.
Okay. Yeah, keep going. Thanks.
All right, final set of results. I guess that's
one more question.
Yep.
So in terms of scaling with data, I'm guessing that hasn't been explored. Have you looked at the impact of like winning race schedulers on your scaling results? I know it looks like you're doing the cosine decay scaling similar to Hoffman, and they do report pretty different changes in what those coefficients are depending on whether the model is run basically past the full decay or earlier in the decay.
Right. Yeah, unfortunately, we have not been able to afford running any ablation on the learning rate schedule. So here, what I'm showing, basically, we use standard settings for vision transformers when it comes to learning rate choices and decay rates and so forth.
And then I guess on these curves, are you showing to the full end of decay? Or is this stopped?
Can you repeat?
So are these training curves run to the end of the winning rate schedule, or?
No, these are stopped at the 5K iteration mark at pre-training.
Okay.
So it's not, yeah, they're not reported at the end of the decay or at, at convergence of the training.
Thank you.
Yeah. Yeah, and again, that was primarily because of compute constraints. Like we could not afford pre-training all these models for 3 weeks at a time.
This is actually a really important issue that we've discussed, right? That if you say right with the the scale that you might have with the AI for science effort, right? I think universities right have hardly a chance, right, to be able to build these kinds of compute optimal laws and scaling and so on. So I think it's a really important question to sort of ponder as a community.
100% I agree with you, Karthik. Yeah. So in terms of running those ablations and experimenting with all those choices and producing scaling laws and so forth, you need a lot of compute to be able to do that. But in terms of pre-training and fine-tuning a single model alone, things are still reasonable. Like my team had access to like 32 to 64 GPUs, and those were enough to kind of build this model. But unfortunately, they were not enough to ablate it to the point that we get complete results for these scaling laws.
Great, thanks.
All right, so final set of results before we enter sort of like the technical part of the discussion. This is a comparison that I guess a lot of people have been asking us for, like how do we compare against sort of the state-of-the-art AI system for weather prediction, which is a GraphCast model by DeepMind. To make this comparison, we fine-tune Aurora at a lower resolution of 1/4 degree instead of 0.1 degree, because GraphCast also operates at 1/4 degree resolution because it was just trained on the ERA 5 dataset. And here we make a comparison against the operational version of GraphCast, basically that is initialized using the IFS HRES analysis data for a 10-day forecast of weather variables. So take-home message is that Aurora matches or outperforms GraphCast on 94% of the prediction targets, so across all variables, pressure levels, and lead times. The biggest gains are observed higher up in the atmosphere, where GraphCast performance is known to be relatively more poor. Large improvements of roughly 10 to 15% are observed at short and long lead times. GraphCast seems to be very competitive at the shorter lead time window of roughly 2 to 3 days, because this is the range of lead times that was the rollout fine-tuning happened for GraphCast. So for that range of lead times, it's still quite competitive. And yeah, the only variable for which GraphCast outperforms Aurora is the specific humidity variable at short lead times of up to 3 days. Similar comparison, I think we have a comparison against weather station measurements, but yeah, that's in the paper. I didn't include it here in the slides. But yeah, the take-home message is, again, all those results I think it's a byproduct of the fact that we're using diverse data to train and we're scaling to a bigger model. So Aurora, in terms of, is trained on roughly 10 times more data than GraphCast, and is roughly 10 times larger as a model than GraphCast. And I think those two are the factors that really lead to the improvements here. There's nothing else in terms of fancy architecture design or anything else. It's just a product of the scale. Any questions before we move into the technical part about architecture details and so forth?
So there are a few questions, but just for everyone's information, so the way Paris is presenting this is he's going through the results first, and then he's going to the technical details, because some of the questions here, talk about, special structure of training, etc., which is what precisely you're going to cover. So yeah, the audience, please keep the questions coming, but I think some of these are going to be answered directly. So I'm just going to hold off. But yeah, every question would be welcome. But yeah, maybe Paris, we can take a minute or two break, just because I want to give you a break. And then, yeah, we can get into the technical part, the architecture and robustness and other things. Yeah, get a glass of water or whatever.
Sounds good.
Yeah, maybe let's start at 10:25 Eastern, which is 4 minutes. So we take a short break, but we'll be back for the second part of your talk.
Sounds great. Thanks.
Yeah.
All right, Paris, we can get restarted. Thank you.
Right, sounds good. So I'm gonna now cover some of the technical details. The high-level picture is that we haven't really done anything super fancy when it comes to, the architecture design, the pipeline design, and so forth. The main sort of approach that we took is that we made very simple choices in how we build the model, and we tried to do the simple things right in order to get this to work. And the main motivation was that we want a model that can be as flexible as possible in the way it can process different data sources, And we didn't want to add any sort of constraints into the architecture. But yeah, let me just go over things step by step here. So again, this is an overview of the Aurora model. You can view it as an encoder-decoder type of model. The encoder is going to accept 2 time steps as inputs. And the inputs could be heterogeneous in the sense that they may originate from a different data source with different resolution, different number of variables, different pressure levels, and so forth. And the goal of the encoder is to take those inputs and transform them into a standardized 3-dimensional representation. So we'll have this latent atmospheric grid in 3 dimensions. And this latent grid will be basically a 3-dimensional collection of tokens. And then we have a transformer backbone that is going to process these tokens and evolve this 3-dimensional latent representation in time. And then finally, we have a decoder that sort of resembles a neural field in the way that takes this latent representation and decodes it back to the different variables at the different pressure levels and so forth. So when it comes to weather data, I showed you all those data sets earlier that we used to pre-train Aurora. At the end of the day, you can view them, the modality is basically images. A single channel of this image has some height and width dimensions corresponding to the latitude and longitude resolution over the Earth. And generally, an input tensor will be a 4-dimensional tensor. Here, I'm only showing 3 dimensions, but we'll have a temporal dimension for the corresponding to the previous time steps that we're using. The number of channels, which is the different variables that we're using. So in the surface, we have a single channel for every variable. In the atmosphere, we're going to have different atmospheric levels. So we have L channels, and then every variable will have, height and width. So here's some example visualizations. On the left, we have the temperature on the surface of the Earth. On the right-hand side, we have the wind speed visualized at different pressure levels or at different heights above the surface, and we have L of them, L heights corresponding to L pressure levels. So the main challenge here is that the width and the height dimensions could be very large. Just to give you a sense, for ERA 5, which is 1/4 degree resolution, the height is roughly in the order of 700 pixels, and the width is in the order of 1400 pixels. But if you go down to 0.1 resolution globally, we're talking about images with resolution of roughly 2000 by 4000 pixels. And if you want to extrapolate, if you want to simulate weather at resolution of 1 kilometer globally, then you would have to process images that are roughly 20,000 by 40,000 pixels. And that's for a single variable, right? For just a single slice of that tensor. So that alone is what makes this problem extremely challenging, because the input resolution of those images increases dramatically as we go to higher resolutions over the Earth. Now, there was a question also about all those different data sources and whether they're available. All the data that we use here to pre-train or fine-tune or evaluate Aurora come from publicly available data servers. So these are data produced by ECMWF, NOAA, and all those major weather agencies. So anyone could actually download all this data. It might take a while if you want to download the whole 1.2 petabytes and you need a lot of storage. But everything, in terms of data sources, everything is publicly available. We did not use any proprietary data in this project. Okay, so I'm going to talk now about how we designed the encoder, which I think probably is the most interesting part of the model, because that's what enabled us to work with these different data sources with different resolutions and so forth. So the inputs, again, is a bunch of different variables. So we'll have some variables on the surface of the Earth. I'm going to use the letter V surface to denote them, so VS. So VS could include temperature, wind velocity, pressure, and so forth at the surface of the Earth. Then we have multiple time steps. So there's the t-axis in this 4-dimensional tensor that, and specifically for Aurora, t was equal to 2. So we use 2 time steps as inputs. And then we have the height and the width corresponding to every variable at the surface of the Earth. In the atmospheric levels, we have this additional channel dimension, which is the number of atmospheric levels, which here is denoted by C. So basically, these are the inputs of the model. So we have a tensor for the surface variables, Vs by T by H by W, and we have a tensor for the atmospheric variables, which is V atmospheric times number of atmospheric levels, which is C, times time times H times W. So these are the inputs. And again, for different data sources, everything could be different. I mean, the time axis is the same, so tip will always be equal to 2, but VA, VS, H, and W could be different from one dataset to the next. And therefore, we need to build an encoder that can operate with inputs that have different, V dimension, C dimension, or H and W. Now, the way we're going to do that is we'll try to take any input collection of atmospheric and surface variables and try to tokenize them. So first, we're going to split those variables into patches. So we're going to take the whole image, choose a patch size, which is a hyperparameter. And the key point here is that we want to pick a patch size that can divide any type of, the input resolution will be fairly standardized, although we have different resolutions. All of them should be divisible by the patch size that we are selecting. So the patch size should be able to kind of divide any input image into a collection of patches. And obviously, high resolution inputs will give you more patches, and low resolution inputs will give you a lower number of patches. But the key point here is that the patch size is the same across all inputs. So here, this is just a standard procedure in vision transformers. We take the image and compute patch embeddings. So we have a collection of atmospheric patch embeddings corresponding to the atmospheric variables. And we have also the surface level embeddings that were used here. So patch embeddings are computed through applying a linear layer. We have a different set of weights for this linear layer for each different variable. And also we have a trainable surface level encoding and atmospheric level encoding that is used to tag the surface level variables and the atmospheric variables at different pressure levels. The way the atmospheric level encoding is produced is that we take the different atmospheric levels that range from 50 to 1000. We perform a Fourier encoding of those. And basically that is added to the patch embeddings that are computed for the atmospheric variables. So this is the first operation that takes place into our encoder. And basically it's just extracting patches and computing those patch embeddings, and also adding an encoding for the surface level and the different atmospheric levels. The second step of the encoder, once we have computed the surface and atmospheric patch embeddings, is we're going to take the atmospheric variables and compress them. So remember, we have atmospheric variables at different levels, and we have C levels in the atmosphere. C could be variable. Let's say in ERA 5, we have 13 levels. In another dataset, we might have 7. We're going to take those variable atmospheric levels and compress them to a standardized latent atmospheric representation, which we call CL here. So let's say if ERA 5 has 13 levels, we will compress them now to CL, and CL in Aurora was taken to be 3. So we're going to have a compression of, let's say, 13, or let's C, capital C pressure levels to a number of 3 pressure levels. And to do this compression, we're going to use a layer called the perceiver. So the perceiver is just a cross-attention operation in which the keys and the values that enter cross-attention correspond to the original atmospheric variables. So we have the sequence length basically here is determined by the number of atmospheric levels, which is C. So now the keys and the values will be sort of like a C by D tensor. And the queries are going to be trainable. So we have these latent queries that are fully trainable, and their dimension is 3 by D because CL is fixed and set to be equal to 3. So now the output of this atmospheric perceiver will be a compressed representation of the atmospheric levels for each variable. So finally, we'll have a tensor that is number of variables times 3 times D, where D here is the embedding dimension. It's a hyperparameter that we choose. So the key point here is that we take the atmospheric levels and we compress them to this latent representation using this perceiver block that basically just reduces the dimension from C to 3, okay? For the surface level, we don't need to do that because it's a single level. So basically for the latent surface, there's no application of this perceiver compression. It's just, we just have the embedding of the surface, essentially. And the next step is that we're going to take this compressed representation of the atmosphere, which is these magenta squares that you see, stack them with the representation of the surface variables, and now we have a collection of what I call latent levels there. And that's what's going to enter the transformer backbone. So that's going to be a 3-dimensional grid of tokens. So we have height, we have width, that corresponds to the patch size. And we have the number of latent levels, which is 3 plus 1, corresponding to the 3 latent atmospheric levels plus 1, which is the pressure level. And before we process this 3D grid of tokens with the transformer, we're going to also tag it with some additional information corresponding to, so every single token will have its own embedding for position, so position on the surface of the Earth, so latitude, longitude position. We're going to have an additional embedding which corresponds to the area that every token covers, because the inputs have different resolutions. So every token could span a spatial region of a different size. So we're going to use the area of every patch over the Earth as an embedding. And also we're going to have an embedding for absolute time. So 3 different types of basically encoding, so position encoding, area encoding, and absolute time encoding. All of those are trainable. They go through a Fourier transform representation, and then they're added to each individual token before those tokens enter the transformer backbone. And this is basically the encoder. And as you see here, this encoder can receive inputs of different resolutions as long as they can be divided by the patch size. Eventually, they're going to lead to a latent representation with a different number of tokens. But that is not an issue because the transformer backbone can process inputs with a variable sequence length. So, everything works as we want. And again, it's a very, very simple sort of collection of operations and assumptions with the goal of taking diverse inputs and transforming them into this common latent representation. So the backbone I'm going to talk about in a little bit, but that's sort of like the boring piece because the backbone is just a sliding window attention vision transformer. The next piece that I want to highlight is the decoder that sort of mimics the structure of the encoder. So the decoder will receive the token grid that the backbone is going to output. And the goal of the decoder is to take the standardized latent token grid and decode it back to the physical variables. So, and again, now we're going to use this type of perceiver layer in the decoding of the atmospheric variables, which is going to undo what the encoder did. So basically, it's going to decompress the latent atmospheric representation and decompress it back to the original pressure levels. And again, it's a cross-attention operation where the keys and the values correspond to the latent tokens that your backbone outputs, whereas the queries are trainable and the sequence length of the queries is equal to the number of pressure levels that you want to decode to. So you could think of this as some type of neural field decoder that uses cross-attention to decode the pressure variables back to the original dimensions. At the same time, we also decode the surface level variables, but that's sort of like a simpler operation. So basically, we just take each token, every token corresponds to a patch, and then we just have a linear layer to map it back to the, to the corresponding output dimensions. So the perceiver here is going to undo what the encoder did, is going to expand this representation of the atmosphere, which is 3 by D or CL by D, and map it back to the full pressure levels, which is C by D. Through cross-attention and using this trainable set of queries. And then finally, all the patches are decoded by linear layers to get a P by P output and assemble the target image at the end. So that's the design of the decoder. And again, fairly simple choices when it comes to that. Like, these are all standard deep learning layers and modules. There's nothing really new here. It's just a matter of putting things together. Same thing for the backbone. It's just a swing transformer with multiple layers, multiple levels that kind of resembles a unit. So we start with this latent 3D grid of tokens. The transformer basically tries to learn a simulator in this latent space, right? So we have the token representation at time, let's say t and t minus delta t, and we're going to transform it to a token representation time t plus delta t. And we have this type of unit type of structure here. The outputs of every encoded layer are going to be fed through residual connections to the corresponding sort of decoding branch. And this is basically just a swing transformer. There's nothing really fancy. So we have a bunch of sliding window attention operations. So we're not doing full global attention, but attention is restricted to a certain window size. And from one layer to the next, basically, we start from a fine grid representation of the tokens, and then we're merging tokens to coarsen the token grid from one level to the next. And also the size of the attention window is increased. So basically, we have these local attention operations. Attention is performed within limited windows, and the attention windows are shifted back and forth between different layers. You see here at every level, we have, the first encoding level has 6 layers. Then there's this patch merging operation to coarsen the token grid, followed by another 10 layers of self-attention, like sliding window self-attention, followed again by another patch merging to get an even coarser grid at the 3rd level. And then there's basically the inverse of this process with residual connections, like kind of like a unit, although there's no convolutions here. Everything is using this sparse sliding window self-attention operation to form this backbone. It's just this conventional swing transformer. There's, again, nothing really fancy happening here. And that's the architecture. So I don't know if there's any more questions. We can maybe come back to that later. Another thing I want to highlight is the data loading pipeline, which is technically one of the most complicated parts, given the fact that we're dealing with these really, really large data sets. So step number 1 is really to download these data sets from all those different public sources and store them in one place. It's really important to co-locate your data storage and your compute. Obviously, you cannot really store all the data on a single node. So the data will live in some type of cloud storage or some blob storage. But it's important that your data storage location is co-located with where your computing cluster is, because you would want to avoid any expensive transfers while you're training the model. So that's one important piece. And then the other important piece is to just make simple choices that work and simple choices that can give you good performance. The way we have approached this problem is that we start with a collection of data sets. All those are stored in the cloud. And then we basically try to stream different data sets to different GPUs during training. So we create a class of objects that we call batch generators. So a batch generator is just a Python class, which is very lightweight. And there's a different batch generator object for different data sets. And each one of those contains, all the metadata that allow you to identify and process different data sets. And then we have a set of lightweight operations for combining different batch generator objects, shuffling them, and then sharding them across GPUs. And then we have a more expensive set of operations that happen locally at every GPU, which is take this batch of batch generators and then unpack them, and then basically feed a stream of batches on every single device during training. And again, we try to keep this as simple as possible in the sense that every single GPU would receive batches from a single data set. And of course, you need to optimize this a little bit in terms of load balancing, but it's fairly straightforward the way this works. So the take-home message is that we're only downloading the data that is required for a given GPU. A single data point here must contain all variables corresponding to that data set and bundle them all together. We're using a file format called ZAR to actually do that pre-processing and bundle, all the variables and the time snapshots that we need together. And then, then you have to ensure that points from the same data sets are batched together correctly to avoid any complications within the architecture in terms of how the attention operations are performed. So, it takes quite a bit of bookkeeping to organize this, but, once you do that, it's a fairly simple pipeline that sort of works well. Of course, there's room for optimization and more sophisticated solutions, but we kind of opted for the simplest possible solution that still performs well in this case. Okay, so this is basically how training works. This is how the data loaders are constructed, and then training is basically optimizing a mean absolute error objective for learning a one-step prediction. So this is the pre-training objective, and then once it's time for fine-tuning, we're going to use this low-rank adaptation piece. So precise fine-tuning strategy will really depend on each task. So from different tasks, we might tweak the fine-tuning protocol a little bit. That'll be atmospheric chemistry or high-resolution weather forecasting. So for instance, I'll just give you an example of what I mean here. For the high-resolution weather forecasting task, that we took a model that is pre-trained on quarter-degree data, and then we want to deploy it on 0.1-degree data. We sort of couldn't fit the 0.1-degree model to memory. So basically, we had to drop off some layers, change the patch size a little bit when we went from pre-training to fine-tuning. So this is really what I mean here, that the precise fine-tuning setup depends on the specific task. You might have to make a few tweaks depending on the task, primarily due to computational constraints. And then finally, the fine-tuning leverages this concept of low-rank adaptation, where we have at every linear layer in our model, so a linear layer is W times X, we're going to fix this W matrix, which is the matrix that we learned during pre-training, and then we're going to only update this factorized matrix of B times A, where this is sort of like a low rank, a product of two low rank matrices to basically add, construct a perturbation to this original weight matrix. So there's a very simple trick, because those matrices B and A are much smaller in size compared to the W matrix. So LoRa is actually a very parameter efficient trick that people employ when fine-tuning foundation models, that allows us to fine-tune with much lower cost and much lower parameter count and help the model adapt to a new task. So again, the model will first be fine-tuned for single-step predictions as an initial fine-tuning phase. And then finally, we're going to fine-tune the model for rollouts, for making predictions for longer temporal horizons. Now, the problem with rollouts is that to produce a full trajectory of, well, let's say, a 10-day forecast, you need to evaluate the model multiple times. So let's say our model is evaluated with a delta T of 6 hours. That means that to get a 1-day forecast, you need to evaluate your model 4 times. To get a 10-day forecast, you need to evaluate our model 40 times. Now, it's really challenging to fine-tune through the entire trajectory, because then basically you have to backpropagate gradients. You have to unroll the whole for loop of evaluations, like 40 evaluations of the model, and then backpropagate through every evaluation. And that is extremely costly for a model with 1.3 billion parameters. You just cannot fit the gradients in memory anymore. So a simple trick that we have employed, and that's motivated by literature in reinforcement learning, is that instead of unrolling the entire autoregressive prediction loop and backpropagating gradients through the entire loop, we're still evaluating single-step predictions, but we use this concept of a replay buffer. So basically, a replay buffer is a buffer that gets updated. Initially, it only includes one step, it includes original inputs and one-step targets. But then as we start training, we start taking the predictions of our model and shuffling them with ground truth data in the replay buffer. And that allows us basically to gradually train the model, starting from short horizon to a horizon of up to 10 days. by only evaluating one-step losses instead of evaluating a loss over the entire trajectory. So it's a very sort of simple concept. So the Ripley buffer, initially it contains ground truth data, but as the training progresses, it contains a mix of ground truth data plus some model predictions. And this mix is randomized, and it kind of gradually shifts from short lead times to longer lead times to capture the whole 10-day window for which we want to make predictions. So this is how basically we deal with the kind of complexity of the rollout fine-tuning piece, because otherwise it's really hard to fit things in memory at this scale. Yeah, so this is the rollout fine-tuning, and I think that's the last bit that I have. Maybe I can just provide a summary and we can take some time for discussion. So the main points here is foundation models are setting a new standard in machine learning in many different domains, in language and vision, but also it seems that even in the sciences, in particular here in atmospheric science and earth system science, there's a lot of potential for foundation models to disrupt this domain. Aurora is the first large-scale foundation model to demonstrate improved accuracy, resolution, and adaptability across a collection of operational atmospheric prediction tasks, so far including global weather forecasting and atmospheric composition forecasting. There's a ton of different next steps. I doubt my team is able to do most of them or any of them, maybe. The first immediate step is acknowledging the fact that Aurora at this stage is just a deterministic model. It just produces deterministic forecasts. A sort of low-hanging fruit extension is to extend it to produce probabilistic predictions, either by training ensembles of Aurora models or by adding a diffusion prediction head or some module that can generate probabilistic forecasts. Another really exciting aspect is the fact that we can use variable resolution data is to also look into local regional data sets at high resolution. For example, NOAA is producing some really unique data like the HRRR and the CONUS 404 data that are super high resolution reanalysis data over the United States. And then look towards enabling high resolution nowcasting capabilities. This whole concept of transfer learning that foundation models bring also introduces opportunities to look into improving weather forecasts in regions where we have very sparse data, like the developing world and polar regions. Of course, the holy grail, as I mentioned at the beginning of the talk, is to have an end-to-end system that basically takes observations as input and produces a gridded forecast. So I think this is sort of where the entire field is heading. So far, we have a lot of exciting work in building just surrogates for the forecasting part, but the ML methods haven't really touched yet the data assimilation part. So trying to combine those two, I think it's a very exciting direction. And then, looking at different tasks, longer temporal horizons in terms of seasonal prediction and climate projections. We have already some proof of concept and motivation that this may work well from the original work, the Climax project. And potentially this could be extended to the more sort of operational setting of Aurora. And I think what we see here is we're sort of like, I view this as a blueprint for building more sophisticated systems that may account for the entire system or multiple subsystems. So start thinking about coupling the atmosphere to the oceans and the land. This sort of machine learning paradigm is very, very flexible in the way that we can start thinking of those questions of multi-physics and coupled systems modeling. There's a preprint online if you want to take a look. We haven't open sourced anything yet, but we're working on it. We have to put a lot of effort in terms of documenting some of the code and producing some examples that users can familiarize themselves with. And finally, I'd like to give credit to the people that actually did all the technical work. And these are the people you see on the left-hand side column, except me, perhaps. And then we have also had some external collaborators and engineers that helped us with the sort of software engineering pieces of the work. And yeah, I'm happy to take questions now.
Yeah, thank you. Paris, this was way more than what we had bargained for. So this was extremely clear and very comprehensive in both the results and um, the technical details. Okay, so there are a few questions. I'll just go one by one. I'll start with the most recent one. So the question is, has there been any consideration for using surface elevation as an additional surface input channel, or is it already included?
Yeah, I missed that part. We do include orography, which is surface elevation, and a few more variables that we call static variables because those don't change with time. So one of them is orography that captures surface elevation. Another one is the land sea mask. And another one, I think, is a vegetation map over the Earth. So those are indeed included as inputs to the model, and we treat them as what we call static variables.
Okay, yeah, thank you. The other question you answered, which is how many parameters does your model have, hardware, and how long? So all of this was in the slides. He was using 32 A100s for 2.5 weeks. So all of that was answered.
Yeah.
Just a quick, and you also showed the parameters just off the top of your head. I saw billion, was it?
Yeah, the biggest model was 1.3 billion parameters.
Okay, great. And then the other question is it possible for Aurora to produce non-physical results? Of course, clearly, yes. But the question is, how do you enforce physical constraints like conservation laws into the model? Because it seems to me that one of the important advantage of numerical models is that they always satisfy such laws.
Yeah, that's a good point. It's a long discussion that we can have around that. First of all, let me start by saying that indeed Aurora is a purely data-driven model. There is no physical constraints. There is a debate on whether you would want to do that or not, maybe to begin with. So, you could think of enforcing physical constraints the way physics-informed neural networks work by adding loss functions and penalty terms during the training. Another alternative way is maybe rethink the architecture design, and I don't know, maybe come up with a different variant of the attention mechanism or something that bakes in certain constraints. My take on this is that for problems where you have access to a lot of data and a lot of high quality data, as is the case for weather forecasting, you wouldn't want to really start imposing a lot of constraints, and you just want to let the data speak. You may ask, where is the physics, and should we throw it out of the window? The answer is no, because the physics is already in the data. So here we use roughly 1.2 petabytes of data that was generated by physics-based models. So all this data themselves satisfy those physical principles that are used to build the PD-based solvers. So the model should learn some physics just directly from the data without imposing any constraints. So the way I view this question is that I see the physical knowledge and the physical priors playing an important role in scenarios where we have lack of data, and we can use that as a mechanism to compensate for the lack of data. But in settings where we have access to high quality and large volumes of data, I think we should stay away from trying to constrain these deep learning models. Now, the question of whether the predictions satisfy physics, of course, they're not going to be satisfying physics exactly, but there have been already some studies that analyzed, I believe it was Pangu weather, that a group analyzed whether the predictions were physically consistent or not. And the answer seemed to be yes. So in an approximate sense, the outputs that Pangu weather was generating agreed with the physical constraints that we expect to be satisfied for this problem. So I would expect that if a similar study was to be carried out for Aurora, we would have a similar conclusion. But again, it's not a strict enforcement of the physics, but more in an approximate sense. And it all comes out because we're training on data that satisfies the physics, because the data is generated by the physics-based models.
Paris, one more question on the same line. The physics can be imposed by data, but also by symmetries, right? So symmetries that are either encoded in how you choose to tokenize the data, or the model architecture which respects symmetries, right? And I think that combination, right, of data and symmetries, and of course, you and many of your team members, right, have done a lot of work on enforcing symmetries with transformer architectures and other architectures, right? I think it's sort of something that is not so well understood by the physics community, right? Because Noether's theorem, right, is not something that we teach routinely, right, to in science. So that symmetry directly leads to conservation laws, right? And if the architecture has the right kind of symmetries and the ways in which you can sort of bring that in, automatically some of these conservation laws are sort of imposed. And I think that is a very fruitful direction. And I think many of the sort of insights that you put in as along both the encoder side, decoder side, and the model architecture side, I think sort of implicitly embed some of that physics in there through symmetries. So just wanted to get your thoughts on that.
Yeah, that's right. So again, in our case, we did not use any equivariant layers, or we did not explicitly take into account any symmetries in the architecture design. Of course, there's a lot of tools out there that can help you do so. I think, again, the approach we took in this problem setting is, we kind of assume that we have a lot of high quality data available, and we would just, kind of take the bitter lesson of deep learning, right? That large volumes of high quality data and large architectures can beat any sort of other approach. And it sort of seems to be the case. The other comment I want to make in this case of weather forecasting, right? Even though we know we can write down PDs and we can simulate them, and of course there's underlying symmetries in play and so forth, the output of the physics-based models that use all that information is not accurate. So it doesn't agree with the observations we're collecting in the real world. So even in this case, it's a question of whether we want to use that information to constrain the AI model. And my take is that we shouldn't if we have access to high quality data. And we should only use it as a mechanism for compensating for the lack of data, not for another reason.
Great. Yeah, thank you. So one other question online is robustness to noise and perturbations. Was there something explicit that was done?
No, we haven't really done any ablations to see that. We've done a few things that may resemble that. For instance, providing the model with incomplete inputs, so just masking parts of the inputs during the pre-training. I think that helps in terms of improving robustness from a representation learning standpoint. But no, we have not tried to corrupt the inputs with noise and see how this affects things. I would assume that intuitively what we see in general in deep learning is expected here. So if the noise corruption is small, it shouldn't really affect much. But yeah, if the signal to noise ratio starts becoming really low, then that will break things.
Right, great. Again, thank you very much for a fantastic seminar and for your patiently walking through all the parts and taking the questions. So thank you very much, Paris.
Yep, thanks again. Thanks for the invitation and for listening to me for 2 hours.
Yeah, looking forward to catching up. I have a few other questions. I'll send you an email or so. But yeah,
Fantastic.
thanks again.
Thank you.
Thank you.